of the day. We have Abdel. Excellent. So he shared his slides already. Can you speak, Abdel, to make sure we can hear you? So we can see the slides.
Yes, sorry, yeah, I made that small.
Okay, no problem.
Thank
So
you,
for the last talk of the day, Abdel is going to be giving this talk through the Looking Glass, benchmarking secure multi-party computation comparisons for ReLUs. And this is joint work with Kashif Navas, Eugenio Salazar, and Victor Zucasas.
Yeah. Hi, everybody. Thank you, Danny, and thank you for being there. I know this is the last talk of the session, and I am the only thing separating you from the coffee breaks. I'm going to try to be as fast as I can. And thank you to the organizers to allow us to do this online. Our wish was to be there and to be able to give this presentation live, but because of circumstances outside our control, this was not possible. Hence, I recommend you to also attending Dani Escudero talk at the ROM session. It's going to be interesting as well. So as Dani mentioned, we are going to talk a little bit about ReLUs today. It's a word that you have heard many times already in this session. And ReLUs typically need two things. They need a fixed point representation or floating point representation, some a way to process rational numbers and comparisons. So we're going to talk a little bit about how you can do that for ReLUs, what is the state of the art, and how you can combine the state of the art to obtain the best results when you implement ReLUs. Okay, so I'm going to go, wait, let me see. Yes, I'm going to go to our first slide. A slide that you probably are going to see like 20 times during crypto. So I'm going to talk a little bit what MPC is. So you can imagine any set of parties, they want to compute a function together, and they want this function to be computed in a way that the inputs of the parties remain secret, and you have some correctness guarantee on the output, okay? The typical way to solve this problem is to outsource it to a trusted third party. So like you give the information to an entity that you trust, it performs the computation, and gives the results back, okay? The magic of MPC is that it allows you to get rid of this trusted entity, okay? So you can imagine that you have a magic box, and in this box, it's not controlled by anybody. This box can perform the operations that I just described. It can calculate the function, it can give you privacy guarantees, and it can give you correctness. So MPC does this in the real world.
Abdel, are you moving your slides, by the way?
Yeah, can you see it?
No, unfortunately, it's stuck on the first slide.
Oh man, let's see. Now?
Now it's moving. Yeah, please continue.
Okay, yes. So sorry guys, like I think I'm not gonna maximize it because if not, it's gonna be like that again. So just to recap, MPC lets you do this in the real world using mathematical protocols. Okay, mathematical protocols. Yes. So now let's talk a little bit about ReLUs. ReLUs are rectified linear units. They are a quite popular activation function. You can find them anywhere nowadays, in not only in the PPML domain, but also in other applications that doesn't require security. Why is that? It's because they are fast. They are good representing data that you would typically do using sigmoids, and they don't require as much of a computational power as you would do for the sigmoids, which is also quite good on the encrypted domain, right? Because nonlinearities are quite expensive. And as long as you can do the comparison fast and you have a way to represent the fixed point arithmetic, you are on the other side and you can get rid of the sigmoids. So how fixed point arithmetic typically works for MPC for an unbounded number of parties? Well, the most typical construction was introduced by Saxena and Katrina. And this was many years ago, and it's the equation that you see on the screen. Okay, where you have some mantissa that I'm gonna call V that lives from 0 to some power 2 to the k, and these are integers, of course. And the precision is given by that p that you see there, the 2 to the minus p. In reality, this V lives on some ring or on some field, this being MPC. For the method of this talk, I'm going to assume this Q that you see at the end, it's a prime, hence this is a finite field. And I'm not going to tell you what is that space in between 2 to the k to 2 to the k plus kappa. It's going to be abducted for the time being. Okay, so everything works well and fine until you come to multiplications. When you multiply two numbers using this representation, you quickly run into a big problem, like that is that the space needed for representing the V expands. So this is where this space that I was mentioning comes into play. This space is typically called slack, and it allows us to use probabilistic masking to bring statistical security once you use this kind of masking. So the authors of Katrina, Katrina and Saxena, they propose a fixed point truncation protocol that allow us to reduce this space. That because of time, I cannot explain this into detail, but it requires the use of slack. They also propose a comparison protocol that also uses slack, reuses the same concept to be able to compare two numbers. In this case, you can subtract these two numbers and compare them to 0. And the protocol is based on extracting the most significant bit. So imagine that your number lives in between 0 and 2 to the k again. If the most significant bit is 0, it means that it's negative. If your most significant bit is 1, it means it's positive. So the trick here is how you produce the masking. The masking is produced as you see on top, where you have to where it's composed by this R prime and this R double prime. The R prime is the randomness up to 2 to the k and is sampled bitwise. Okay, so we use the random masking again that uses slack, and this allows us to have this complex equation somehow that it's capable to determine what is the most significant bit. And the most important thing here is to notice that there is a comparison inside this equation, but the interesting thing is that that comparison is against the R prime, and the R prime was sampled bitwise. So this allows us to use a bitwise comparison that can be taken for that can be implemented using any binary circuit, and it's not quite efficient, but you can obtain it that way. And that is how Katrina and the Hog in this case decided it would be a good way to use this. By the way, these two protocols are extremely commonly used. You can find them in Scale Mamba, in MPSpeeds. They are everywhere. And this was 10 years ago. I think 1-2 years ago, Rabbit appeared. Rabbit is a little bit different. The comparison here is in absolute terms. So there is no concept of positive and negative. And the comparison is done against some R. And this R is a public constant in the domain. In this case, for the authors, the domain was bounded by some M. That's why you have an M in the end. And an important detail is that the R is sampled bitwise. Okay. The method exploits the commutative properties of addition. So it produces a couple of equations using the following elements. First, the X mask with the randomness that is called A. Then the V, that is basically the A plus this capital V that you see there. And then DC. Together, when they are mixed up, and for some process that I'm gonna also abduct from this presentation because there is no time to explain, you come up with these three basic comparisons that when are added in the way that is stated there, gives you the X is smaller than R, okay? One of these is public, the other two contain secret data, but the secret data is R. And as I said to you, the R is being sampled bitwise using EDA bits. Hence, this can also be performed using a Boolean circuit, okay? If the M, as I said at the beginning, is a prime number, then the sampling on R bitwise has some trouble, right? So in this paper, what we try to do is to take all the stuff that you saw, try to mix it up so that we produce the fastest comparison possible. And we also use state-of-the-art elements to evaluate the bitwise comparisons that you saw there. For that, we use something called SAPHOT. It's an MPC mixed protocol contribution of a couple of years ago. It allows us to mix HSS17, which is something akin to VMR to evaluate garbage circuits in a distributed fashion, and full threshold implementations of arithmetic circuits like speeds, like overdrive speeds or whatever variation of speeds you want. And it allows us to do that in constant rounds. So it's amazing. So the first thing that we did is to try to use SAPHOT with Rabbit. As I said to you, there is a problem with the sampling. The problem with the sampling is that it's done bitwise. So hence, we use two techniques that the authors succinctly mentioned in their paper, rejection lists and using a prime that is close to a power of 2. And we use the SAPHOT techniques and DA bits instead of EDA bits for the sampling. Then we incorporated also a SLAC into Rabbit, and we changed fundamentally Rabbit. We use the random sampling from Katrina, and we use SAPHOT for the evaluation. And finally, we come up with something that we call Beyond Katrina. It's a unique protocol in the sense that it uses the fastest less than implementation from Rabbit that we have to also adapt, the flow and the random sampling from Katrina, and the evaluation from SAPHOT and the DA bits for sampling. The circuits were also compiled using VHDL and then transformed to Bristol fashion so that it can be used by the framework later on. So our testbed is quite simple. 5 machines, they see each other. We use a scale Mamba 1.14, and then we did extra modifications on a scale Mamba so that we can use something that we call offline garbling. So SAPHOT is reactive, which means that garbling also happens online. We modify it so that we can pre-garble the circuits in a pre-processing phase, and then do the evaluation of ReLUs as well. We also compile the circuits, as I said, using VHDL, the original circuit, and then we use hardware synthesizers to try to accelerate the circuit execution as well. And this is the takeaway. So this is a time map. The orange box there is the time that it takes using to execute a ReLU using MPS bits with the typical comparison that is implemented there, that is Katrina. As you may see, it's quite significant when you compare it with the fastest version of Rabbit that we have, that is Rabbit SLAC, that is actually much faster than Katrina. And if you use beyond Katrina, you can even reduce the times further. And if you use the offline garbling, that is 80% faster than beyond Katrina. The improve was quite astounding when we finally implemented this. But to be fair, these are the timings for all the methods. So typical Rabbit using a rejection list and with a power of 2, they were the slowest ones. But you have to also bear in mind that Rabbit implemented with a rejection list has perfect security. So that's a super nice characteristic to have. This is the chart that you saw above. As you can see, the difference with the original Katrina is quite significant. But if you take only Rabbit, SLAC, and beyond, you can see that when we use the hardware accelerated version, the results are much better. So these were tests that we performed in 2 machines. We introduced in the chart that you see on the right, we even introduced some delay instead of just having the 2 machines talking to each other. We have some artificial delay. So thank you so much for your time. The paper is available. We also have a repo with all our resources, so you can use it if you want. And that's it. thank you again for all your time. And again, please go and see Danny's talk at the ROM session and enjoy your coffee break. Thank you.
Thank you so much, Altea. So you did receive an ovation as well, of course. So one quick question from the audience, if there is any. So just a quick question of that, like, is there any difference between fields and rings in your protocol?
Well, not really. Like, not really. You can use anything that you want. But in this case, it was simple to explain it using init fields. More evident, yeah.
Okay, no, that's great to hear. So let's thank the speaker again, please.
Yeah.
And